you're here to listen to a talk about Microsoft Secure Channel, and you might be wondering what RDP has to do with Secure Channel. Well, Secure Channel is the TLS library for Windows, and RDP uses that. So that connection that we just saw uses an ephemeral key exchange, and at the very end of the talk, the demo is we're going to decrypt that. So in the meantime, the VM that I just logged into is just going to sit there running, and again, we'll explain how that all works. So very quickly, what do you get out of the talk? Well, I just told you. We're going to be able to decrypt sessions that use TLS sessions that use ephemeral key exchanges, and we're going to be able to pull the private certificate and the session ticket key directly out of memory as well. And then from a forensics perspective, it's kind of cool. We can map public certificates / server name indicators, both of those, to a process ID and a logon ID. And I'm not talking about like a user ID. I'm talking about the logon session ID, which is unique per each login. So let's talk about how we get there. Very quickly, we're going to go over TLS and SSL. I know you all know what that is. You've seen it a billion times, but it's Saturday at DEF CON, so a few brain cells lost. We're then going to go through S-channel and CNG and what those actually are, what those words mean, and how they relate to what we're going to be doing. And then we'll talk about the secret data and all the things we're going to pull out and the forensic context. And then finally that demo. So quick disclaimer, it's not an exploit. And actually, Microsoft hasn't done anything wrong, despite what we're going to be able to do. For the most part, there's one kind of exception to that we'll talk about, which is a little like, but mainly just implementation-specific oddities. And then Windows isn't going to track sessions for processes that don't use their TLS library, which should kind of go without saying, but just full disclosure. And also, things that aren't TLS aren't going to be tracked either, so things like TeamViewer don't get tracked. So you're probably wondering, well, what does? Well, again, Internet Explorer, Skype, everything that you saw in the intro there, LDAPS, and then third-party products as well, anything .NET, and then third-party products like GoToMeeting and things like that. So, cool. Background. What is this TLS thing that we all know what it is? So, I'm not going to walk you through the handshake, but the thing that we need to pay attention to for the purposes of the talk are there's a key exchange that happens, right? That key exchange gets dictated in the cipher suite. So you have an example cipher suite at the bottom. TLS is the protocol. ECDHE is the key exchange. It's not actually a key exchange, it's just an exchange. And no matter what, we're going to have a client key exchange that happens as part of whatever key exchange we have, whether it's RSA or Diffie-Hellman or whatever. But what that looks like is going to change. So, and it's also going to change what's in memory. So we're going to focus on RSA for just a second, and then we'll move into the rest, and there's a reason for that. But basically, if we're doing an RSA key exchange, server in the hello says, proof of who I am, here's your public certificate. Client yanks the public key out of that certificate, generates random data. That becomes the pre-master key, encrypts that, and ships it back to the server. The server then uses the private key to decrypt that, and voila, we have a shared secret over an insecure channel. Very cool. Except the shared secret is going to be different depending on the type of key exchange we use. So if we're not using RSA, it's going to be a different length because it's derived differently. So then we turn that into a master secret. And the master secret is actually our shared secret that we're going to use to derive session keys each time. We're just going to mix in some public values and stamp out some session keys and start doing our symmetric crypto. So that's all good and well, but it kind of takes a long time. Especially if you've got those clients that are just pinging you constantly and it's the same client over and over. So the guys that wrote SSL thought of that and they decided that, well, let's do this. Let's implement something called session resumption where since we've already done it once and done this, the full key exchange once, if we store that for just a tiny period of time, just a little bit, then we can actually resume that. We can see a huge performance benefit. So how that works is basically the TLDR handshake is hi. The client comes up and says, hey, remember me? You gave me the session ID. We met at that party. It was awesome. You've got that secret that I also have. Can we talk? And server says, fine, okay. And then they mint out those session keys again using that shared secret plus client random to then speak via an encrypted tunnel. So that's all good and well, but you kind of remember we mentioned RSA. Well, there's this whole problem with we're sending that private key or that pre-master key over the wire. That's not good, right? Because in theory, because the private key itself is sitting on disk, we can then decrypt that later. And everybody's known about this for a while. So long, in fact, that Whitfield Diffie of the Diffie-Hellman key exchange, back when DEF CON started, put out a paper that said, RSA is probably not perfect forward secret. And what does perfect forward secret mean? Well, what it means is if you and I are able to, the property of perfect forward secrecy is essentially if you and I are able to successfully exchange secret material once, and it's secret at that time, at no point in the future should anything compromise the security of that exchange. So if a bad guy captures us, is listening, and later on he gets the private key and can decrypt that, which is how it's historically been done, that's bad. That shouldn't be able to happen. So they actually, instead of exchanging something private that was a secret over the wire, they actually just use public values and the commutative properties of exponents to actually exchange only public values and derive a shared secret. So there's not actually a key exchange, it's just sort of a derivation process. But that's all magic that we don't need to talk about. What we care about is the basic principle is we shouldn't be sending anything over the wire that's secret, that's over an unsecured channel, and we shouldn't be reusing keys, especially not something that we store on disk, right? And to take that to its logical conclusion, we should actually use a key once and then throw it away and never use it again so that we insulate all those connections. So if you're truly perfect forward secret, that's what you'd have to do. That's not actually what happens, of course. The TLS spec allows for session resumption, which is what we talked about. So it's not storing something on disk most of the time, but it is, we're not talking about the private key anymore if we're using like an ephemeral Diffie-Hellman exchange, but we are still caching those master secrets, and because we do that, and in fact the spec allows you to do that for 24 hours, then we can still, within that time period, go back and decrypt that session retroactively. Or if we grab that out of memory before that time, whatever that cache timer is, expires, we can then decrypt future sessions as well because we now have that shared secret and, in fact, potentially do bad things with them. So that's one of the problems with TLS. The other one is obviously we talked about RSA, but there's this extension called session tickets, which you've probably heard of as well. And the basic principle is I, as the server, don't want to have to deal with all your client crap. I don't want to store your master secret, so I'm just going to encrypt it and send it back to you. Well, just like sending the pre-master secret, if we're sending the encrypted master secret back for the client to store and then pass back to us when it wants to resume, that's kind of a problem. The benefit of it is essentially that now you can have multiple servers that you load balance and they can resume each other's sessions if they just share that one session ticket key that's in memory. So we're back to the problem with RSA, but we're just using a more ephemeral key, basically. And then on top of that, so that's just what TLS allows and just kind of the normal go through. But there's also implementation-specific oddities, and we're going to get into that today, specifically with Microsoft, like storing symmetric keys. Symmetric key schedules. So the key itself is random, but the key schedule isn't. And also, we talked about how you should really just use that ephemeral key once, but there's a little bit of reuse that happens, and we'll see if that's, is that perfect forward secret or is it mostly perfect forward secret? So the title is S-channel, soliciting S-channel, soliciting secrets from S-channel. So what is S-channel, what is CNG? So secure channel is, again, Microsoft's TLS library, and it gets loaded into the client process that actually wants to do the TLS exchange, but Microsoft doesn't really trust you and your little C# web server to use their private keys. So they maintain and encapsulate all these keys in a security process called the key isolation process. So if you've ever worked with Windows security, you know what that's going to be. It's LSAS. And so S-channel itself, again, gets loaded into both of those, and then once the key change happens inside of LSAS, it passes back the security context for the connection that has all the parameters, and it passes back a handle to the AES keys, the symmetric keys, so that you can actually manage that tunnel. But it doesn't actually handle any of the encryption itself or any of the ciphers itself. That's all handled through the CNG, which is the CryptoAPI next generation. So CNG, again, next generation is always the best generation. It was introduced in Vista, so believe it or not, there's a use to all those years of blue screening that you had to deal with. It brought around things like AES and elliptic curve crypto to Microsoft and really modernized their capabilities as far as cipher suites go. And CNG basically has two functions. It stores things, and then it encrypts and decrypts things. So the encrypting and decrypting is done via DPAPI. Again, Ellie Burstein, who was in Vegas recently, he's the guy who did all the seminal research on that, so I talked to him. And then, but we'll go over it as well. And then the key storage providers actually handle the storing of those secrets. So what does that look like? And quickly, okay, so that's all good and well. Does S-channel actually embrace perfect forward secrecy? And the answer is yes. Microsoft has embraced it after the introduction of CNG. So again, we talked about how they introduced CCC. So what you see in Vista, their preferred cipher suites, they don't prefer ephemeral suites. They don't prefer elliptic curve suites because it was just introduced and Vista was broken enough. And then in Windows 7 and Windows 10, they actually switched to just preferring those. And you also see that this metric suite that we prefer, this metric cipher that we prefer, becomes almost exclusively AES. So that's all good and well. And basically what that means is that we can't do that. We can't use that old RSA trick of just grabbing the private key off disk anymore if we want to decrypt things. And that's why that's part of the reason that Contextus, I think, open sourced their RDP replay tool that we're going to be modifying and using later. So we know that we can't use the RSA private key to decrypt things anymore, for the most part with Microsoft. And we know that that in theory TLS allows you to cache things. So does S-channel cache things? Well, their documents say yes, it does. There's a master secret, the cipher suite, and certificates all get stored after the first connection, after the first handshake between a client and a server. And additionally, you see in their documentation references to the fact that LSAS consumes more memory. They tell us roughly how much it consumes, so we get an idea for what this cache might look like, how big it might be. And then they mention that by default, S-channel, or yeah, LSAS is going to store 20,000 entries. So that's maybe not a lot for a server, but it's a lot for a client, and a reasonable amount for a server. So how does S-channel actually operate? This is a very complicated looking Microsoft diagram that I made pretty. Oh no, we're good. And it hides a very simple truth, which is essentially that regardless of whether you're a client or a server, it happens exactly like I explained before. Client wants to make a connection, says, hey, LSAS, please give me a security context and some symmetric keys. LSAS does the key exchange, and on both sides, that exact same process happens if they're both Windows servers. So that kind of gives us an idea, again, of where we want to look and where we might find things. So CNG, how does that work? Essentially, everything gets routed through the encrypt DLL. That's kind of really useful for the reversing aspect because that kind of told me where to look. And then there's this whole key isolation service, and then we have these key storage providers again that then manage those secrets in memory and on disk. So just as a quick summary, we're looking in LSAS, we're looking for secrets and keys, and we're doing that because that's where the handshake happens, and because S-channel prefers ephemeral cipher suites in the handshake. Cool. So again, why do we want to do this? What's the value? Well, we want to be able to subvert perfect forward secrecy. That's the point. Like, now that we know that S-channel embraces it, we want to get around that. We also, even if we can't do that, we want to see, is there any forensic context to be had, and is there anything we can do with that that would be of value, and how long does that live? And then finally, again, from a bad guy's perspective, it's kind of cool if we could just get access to a single process and dump out things we need to decrypt things in the future and in the past, and be able to impersonate the server if we can pull out the private key, maybe, without touching disk. So what do the secrets look like? So again, based on what we've all talked about right now, we basically have session keys, we have a master key, pre-master key. Those all exist on the client and the host after that initial exchange, key exchange. Well, through the process that we talked about. And then on the server, there also could be an ephemeral private key if we're using an ephemeral suite. If we're just using RSA, we'll have a persistent private key. And if we're using session tickets, there's going to be this session ticket key, right? So that's all the possible secrets we could have for a TLS connection. And what do each of those get us? Well, again, we talked about the fact that session keys are short-lived. They're not going to get us much. We're going to get a single connection. The master key and the pre-master key are going to get us a single session. And then the ephemeral key and the pre-master, the ephemeral key, the private key, persistent private key, and the session ticket key will all get us multiple sessions depending on what we're using. And then on top of that, there's that persistent private key usually gets used for signing as well, so that'll get us identity for the server. So what do we get? We got them all. We got everything. So what you see up there is the paths to the keys that are sitting in memory, inside LSAS memory. And they're named based on either the name I gave the structure that I reversed, or on the symbol name that Microsoft has for the respective structures. So anytime you see an unlock symbol, that means that that secret is sitting unencrypted in memory. And obviously, I know everybody goes straight to the one that's got the lock sign, and they're like, what about that guy? Well, we're going to get to that. That's actually not a problem either. And then the one other thing, obviously, is we see the pre-master key down in the corner, pre-master secret, sorry. And you're probably saying, well, you're cheating. You said everything. What about that guy? And we'll explain that too. So how do we get to that point where we have everything and and we know exactly how to get to it? Well, I started with the session keys because it's closest to the data, it's most ephemeral, it's not going to be encrypted because it's a symmetric key. That would be kind of wouldn't make a lot of sense, at least not in software. So I started with AES because, as we saw, Schannel prefers AES for everything. But AES keys are small and random, so I mean that's kind of a non-starter, right? Well, not exactly. So smart guys over at Princeton a while ago wrote a paper called cold boot attacks, and they talked about the fact that a lot of implementations store this key schedule. So AES gets expanded into round keys, and that process is deterministic, hence why it's called a schedule. And because of that, we can actually take that otherwise random data, we can calculate what the next item based on that random chunk that we're looking at would be, if it would be part of the schedule. And if it is, then we have a really good chance that we have an AES key. So I basically just scanned the client and server process, and what you see there is matching AES keys on each. So what does that give me? Well, that allowed me then to go look at those offsets in memory and start figuring out what the context of those were and how those were stored. You see that there's 4 keys stored there. That was actually 2 separate connections. And remember that when we're talking about TLS, we have a server write key and we have a client write key. So there's going to be 2 AES keys for each. But yeah, so one thing that I noticed when I was doing this, and this is what the data structure looks like. So one thing that I noticed when I was doing this was that there's this magic value, 3LSS, which is actually stored as a D word. So flip that around, and that's a little endian, and it's SSL3. And I was like, aha, eureka, SSL3. This is, this is cool. Maybe, but it was weird because I was a TLS 1.2 connection, so I was like, maybe they're just terrible at their naming conventions or something. But I started scanning for SSL2 and SSL1 and everything else. And what I was actually able to find was that there's SSL 1 through 7. So it's not the TLS version. It's something else entirely. But before we get to that, just quickly to go over this structure. The session key structure itself has this magic value. Right above it has a length value. It's got the protocol version, which is the TLS version. And then it's got a pointer to the cipher suite list, so we know what kind of key we're looking at, basically. And then at the very end, there's a Boolean flag to say whether or not it's the right key for client or server, basically. And at the very end, there's a pointer to a decrypt key structure. And if you've ever played around in the back end of Mimikatz, you know that decrypt keys are used everywhere in LSASS. They're superfluous. Not superfluous, they're just everywhere. And Benjamin Delphi did a lot of research on reversing those. I actually then did it myself because I didn't actually look at the source code until after I'd kind of gotten into it. But yeah, so these things are kind of consistent. And then on top of that, he calls this MS symmetric key, he calls it like a decrypt key, and I think he calls the other one a decrypt key handle. But the reason I call it that is because of the symbols in memory. There's actually a validation function that says, for this magic value, MSSK, validate symmetric key. So it's Microsoft symmetric key. And then the thing highlighted in red is the actual key itself. Cool, so I mentioned these magic values, these SSL values. How do these come into play? Well, when I started looking at the modules for these magic values just to see if I could pull apart the functions where they were stored or that generated them, what I noticed was there's a few really, really quick validation functions that literally just do 3 things. They accept a pointer, they check the size value of the structure at that pointer, and then they check the second value for a magic value, which is that SSL, 3 or whatever the number is. So, so by dumping out the rest of those and then kind of looking at them, they're all the same. And what that gets us is it gets us size values and function names that are very descriptive for specific structures. So we kind of know now that this SSL5 magic value is going to be tied to a master key. And we know that SSL4 is going to be tied to a key pair, whatever that is, which turns out to be the private key. And then SSL6 is for the ephemeral key. Now, SSL3 didn't actually have one of these. I just happened to come across it when I was looking at other functions. But we do see that it gets used in decrypt, encrypt, generate session keys, and also I've just traced through and I know that those are the session keys. So the only other one up there that doesn't have anything is the SSL7. And that is the pre-master secret. So pre-master secret we don't actually really need because it literally is per connection and gets used only to generate that master secret that's always going to be the same length because the pre-master secret's variable based on, again, what key exchange we're using. If we're using ECC, it's going to be the x coordinate of the shared secret that we derived. So basically, it's vestigial. We don't really need it. We have if we can get the master key, which we can get. So SSL7 is only used for the RSA pre-master secret. And on top of that, it gets destroyed very quickly. So they actually follow the spec on this. As soon as you've got the master secret, you destroy it, so you'll never see it in memory. It's kind of too beautiful to live or whatever. So master secret. Basically, this is the Goldilocks secret. This will get you multiple connections. It'll get you the whole length of a session. This is what gets cached. Microsoft told us that in their documentation. And it's delightfully simplistic. Basically, it just stores the master key directly in an array as part of the structure. It tells you the protocol version, and it tells you the cipher suite that you chose, because obviously we need to take that master key, mix in some stuff, and mint out some session keys. But yeah, so incredibly simple. But the problem is, and if we just have this right now, we could actually then brute force a given session ID with that master key, with all the master keys in memory, and potentially be able to decrypt it. But it would be a lot more elegant if we could map it back to a unique value, which is what we really want to do. So this is what that looks like in memory. And what you're going to see as we go through is there's going to be a lot of WinDebug. And the reason that I did that is I have the full commands there. So once you have the slides, you can actually go through and validate my work yourself. Or you could do it as you go along if you want. But yeah, so that pointer, again, points to a Unicode string and points to the identifier for the cipher suite version. But there's no other pointers out of the structure. So we have to figure out how we can map this to a unique value. What do? Well, you scan for pointers to the structure, right, in memory. And what I was able to find is kind of similar to how the bcrypt keys work, encrypt keys, which I'm guessing means network crypt keys, have a handle that then points to that secret. And if you go back from that, you actually get to the session key structure. And I kind of found it because I was able to see session IDs directly below. And you might be wondering, how did he see session IDs? They're supposed to be random. Well, they're not always random, actually. They're just arbitrary, and we'll get into that too. But basically what we have at this point in time is we have plain text. We can go from a given session ID all the way through to a master key, and we can then decrypt the session that belongs to. And we can do that by just, the quickest way to do it is really just to dump it out in Wireshark format and open up in Wireshark, and it's instant gratification. So, which is exactly what we like. So yeah, so now we have the master key, and we could really stop there, the master secret, sorry. We could really stop there at this point because, I mean, we can decrypt sessions, that's great, but why do that when there's other things to be had? So there's this ephemeral key, right, and this persistent private key, and depending again on the key strings that we use, they're going to be, one may exist or one may not exist. But they share the same structure because they perform the same function. So there's this SSL key pair structure that, again, has a magic value of SSL4 or SSL6. That points to an encrypt key handle, which is not really the same as that encrypt SSL key that we saw. It's got a different magic value and slightly different structure. And that points to this KSPK structure. And you're like, that's not how you spell key storage provider. But it's because it's backwards, and again, because it's a little endian. So this KPSK structure is the instantiation of the key from disk or the ephemeral key itself. And it has all the values we need to do anything interesting with them. So that is the key storage provider key, and it's kind of the thing that we're shooting for. So the ephemeral private key itself, that's what it looks like dumped out. It's stored little endian. Nothing else from Microsoft is stored little endian for the keys and the secrets. So it kind of threw me off at first. But what I did there is I dumped out, based on this ephemeral key data class, I dumped out the public key and then the generator values from the KSPK structure, so from that key storage provider structure. And then I dumped out the private key. So you could basically then, assuming you knew the large prime value, you could take that private key there and then generate that public key to verify that it is in fact a private key. So it's stored in this MSKY structure, which gets used later on in the talk. And basically, once we have this, what can we do with it, right? Well, Wireshark doesn't support ECC keys right now by default, just to decrypt things like it does with RSA private keys. But it doesn't. There's no reason that it can't. Once we have this, we can drop it into a pen structure, and we can kind of use it as we want. And because it gets reused and it gets stored in memory, this gets us multiple sessions, and it's kind of great. So it's the equivalent of what we would have had before with the RSA key if we were using an RSA key exchange. So then the persistent private key itself. So now at this point we have all the ephemeral things, in theory, other than that whole session key thing that we'll get to. But what about impersonation of the server? What about that thing, that little lock symbol that wasn't unlocked that you guys are like, yeah, he's cheating? Well, the RSA key gets pointed to directly out of one of those KSPK structures, the key storage provider, and it's encrypted in memory. So it's encrypted with DPAPI. Well, if you've ever done anything with DPAPI, or if you've ever read any of, again, Ellie's work, you'll know that because it's encrypted as a system secret, we can actually just grab that system secret, decrypt the DPAPI master key, and use that to then decrypt this blob. So You could go back to disk, you could grab that, and you could then just decrypt this, but what's the fun in that, right? Because we want to be able to get this straight out of memory. Well, up there you see highlighted in red is the key GUID out of the DPAPI blob. So what I did here was I scanned I just scanned memory for the master key list, which basically the master keys for DPAPI get cached in memory, but they're encrypted. So Benjamin Delphi did a lot of work on this, and again, this was one of those things where I looked into it, and he beat me to it, and he's just a badass. So basically what you can do is you can take the, there's symbols that point to the initialization vector and the symmetric key that then encrypt these master keys. You can encrypt those, and then use that to encrypt the blob straight out of memory. And when you do that, you get this. So on the one side, we have the RSA key from disk itself. On the other hand, we have what we decrypted out of memory. And you'll know you've done it right if it's an RSA key, because the Microsoft structure actually has this RSA2 magic value that you can just see. So, so at that point, now we can directly impersonate the server without having to touch disk, which is kind of cool. So what about that session ticket thing? That's like the last thing that, last secret that we have to go over that we haven't really talked about yet. So it's not really seemingly in widespread use. It seems like the support for it's a little bit, well, a little bit lacking. But well, at least the documentation is for sure. So sometime around Windows 8 and Server 2012 R2, Microsoft basically enabled the capability to use RFC 5077, which is the session keys. But they didn't actually provide any documentation with how to use that. They did push out these PowerShell functions that you can use. And what I've done there in that example is I've enabled those PowerShell functions, or I've ran those PowerShell commands that they give you as examples to create a administrator-managed session key, ticket key, and then enable it for the account. But that doesn't actually enable it for the system, and they don't tell you how to do that. But what they do tell you in the Windows 8.1 release preview release notes is set this value to disable session tickets. It's screwing things up. So taking the opposite of that, I set it, instead of to 2, set it to 1, and then next thing you know, I'm able to actually use session ticket keys. So up till this point, even though things have been unencrypted in memory, and even though we can do bad things with them, and that's cool, or great things if you're a forensic guy, Microsoft hasn't done anything wrong. I mean, realistically, those are short-lived keys, so in theory, like, it's fine to keep them unencrypted in memory, and then the one thing that does get stored on disk that they pull into memory, they then encrypt, even though they store the keys to decrypt it. But the session ticket key is kind of that thing where they kind of mess up a little bit in my mind. But if this is, in fact, the Microsoft-approved way to do it, which I can't say that it is, the administrator-managed session key gets stored on disk, and it gets DPAPI protected, right? Just like any other key that gets stored on disk. So we can then pull that out. And that key then gets derived, or gets turned into an AES key through a key derivation process. But that AES key is actually the same AES key across reboots, which basically means that if you enable session tickets, and it happens at the S-channel layer, which means that it happens for all services in Windows, not just for IIS, it happens for IIS and RDP and everything else we talked about, then if you can pull this key off disk via, I don't know, the export TLS session ticket key function, commandlet from PowerShell, you can then decrypt these just like it was an RSA key. You can then decrypt those sessions, which is kind of crazy. So, so yeah, they do cache this key in memory as well, so we don't have to go to disk to get it once we export it. But what we can do is we can pull it out of the cache, and there's no symbols for the cache. But if we have the key GUID, which gets stored in the session ticket that gets sent across the wire, then we can actually just reference that because we know. Because I know what the structure looks like and I know the offset. So what do their session tickets look like? Their session tickets are actually, they're cool. They flip the MAC above the encrypted state, so they don't have to change a bunch of things if they change the size of the encrypted state, which is great. And otherwise they follow the spec. But because they have the IV in there, which is that they're supposed to have, and because they have the key GUID, and because we can pull that key out of memory, we can then go directly from having something on the wire to what this slide shows, which is decrypting that session ticket and seeing what that value is. And as you'd expect, it's just got that master key structure stored inside of it, along with things like a timestamp and TLS protocol version and things like that. So, so yeah. So at this point, we basically decrypted all the possible secrets that we need out of memory. So secrets are cool and all, but what if you don't actually have a packet capture? What if you don't want to decrypt things in the future? What if you don't care about any of that? You just want to know how this relates to forensics. Well, that's why we have the context. So, core TLS SSL functionality that provides metadata that we can use. Well, timestamps typically are the first 4 bytes of the random values that get generated if you're following the spec. And then there are other things like obviously the public key can be used for fingerprinting the server, but the session ID can also be used for fingerprinting the server because Schannel uniquely creates these, takes the first D word and then performs an operation on it as said by these people that wrote the dual EC paper, so that the 2 bytes, the first 2 bytes are random, the second 2 bytes are 0, and then the rest of it's random. So you get a very visually recognizable pattern for the session IDs. And then on top of that, obviously we have what TLS extensions offer themselves. So we have this concept of server name indicator. And the cool thing about that is if we just run something like conscan with volatility, we only get the IP address and we get the port that it goes to. But because we have the SNI, if it's a virtual host, and because we have the public key, we can then say, okay, well, this is exactly who you're talking to, or who you were talking to, not just the IP that you were talking to. So how long does this whole thing actually get cached? We talked about what the spec allows. How does this actually work? What are the actual values? So there's these values get stored in memory, the client lifespan, server lifespan, and the session ticket lifespan, and those are all 10 hours by default. So what that is the maximum time that you'll have one of these in memory. So you don't get the full 24 like that you could get in theory for session ID lifetimes in the spec, but you do get 10 hours, which is still a lot, especially if you're a guy doing IR and, I don't know, somebody RDPs into your machine and then you get an alert on it and you want to go back and potentially pull the memory from that machine if you dumped a packet capture. So the other thing is the maximum number of entries. So again, this is hard-coded into the Schannel binary, just like that value above, but you can override it in memory, or you can override it in the registry. And that's set to 20,000 entries by default. And then the other thing is enable session tickets in theory, it's 1, 2, or 0. Presumably 0 is undefined. That's what it is by default, hard-coded into the Schannel binary. And if you don't change that to 1, then session tickets don't seem to work. And then there's a cleanup interval, which is how often this cleanup thing runs. So if you, as the process, decommission or purge your cache, then there's a possibility it might stay around for a tiny little while before that timer expires. So as the process, you have full control. Schannel is still just the library. So the processes can purge the cache whenever they want. So you might not get a full 10 hours. It kind of depends. And the other kind of unfortunate thing is that because we're centralizing this and because we track the processes themselves, if the process dies, it seems that the cache gets completely cleared for that process. But things like RDP, things like IIS, things like most of the sort of services that we're interested in, even something like Outlook runs as a service. So you aren't going to have that problem, basically. But they might also decide to purge the cache periodically at their discretion. So what does the cache actually look like? Well, as you see, as you saw when I was talking about the keys, there's a lot of these symbols have a C prefix in them. That's because they're a C++ class. And so the virtual function table gets stored at the top. And what that enables us to do is if we can use symbols, we can actually just scan for instances of that function in memory, which is kind of cool. So the very first thing that gets stored is that VF table. The next thing is a pointer to the master key. And again, I haven't got the whole structure there, which is why this is like a V-type, a volatility V-type. So it just shows you the offsets to the things I know about. You also have the process ID and then that logon session UID that I was talking about earlier, which is kind of cool. And then the session ticket or the session, there will be a pointer to the session ticket if session tickets are used, or there will be the actual session ID itself stored as an array directly in that structure if that's what's used. And then on the server side, it's a lot smaller. You're not going to have session ticket pointer because they don't get stored on the server. But you'll still have that process ID and those other kind of useful things. And then just because I had time, well, didn't really have time, but just because I felt like I wanted to be thorough, I also went and looked at Vista. And basically, Vista's kind of it's before it really becomes more object-oriented, so it seems. So it uses just a list structure. So once you find one cache item, you just loop through the list entry, and you can find all the other ones, which is nice. So yeah, so that's cool and all, but how do we automate that? How do we actually make that useful? So what I'm providing is a volatility plugin, and I'm providing a recall plugin as well to automate that. And by default, it's just going to dump out that Wireshark format we showed earlier. And then what I'd like to do, too, is hopefully talk to Benjamin Delphi and see if he's interested, or maybe create a PowerShell module that'll do it live, so you can actually just do it live as well. But yeah. So limitations, we're working with internal undocumented data structures for the most part, which means that they're subject to change. Sometime in I think it was March or April, there was something that was inserted midway through the cache. And so you get to this position where you have, maybe some hosts that are updated and some that aren't, and the cache is going to look different, which is kind of annoying. But it happens below the, or I suppose after the session ID, so you don't really have to worry about it for session IDs. It does affect how session tickets get parsed. You can still do it. It's just harder to detect that in an automated fashion. It'll take a little bit more. It'll be a little less clean. And then we're relying on symbols. So Microsoft gave us symbols to do some of this pretty easily. They can also take them away, which is totally their right. But realistically, that probably isn't going to have that much of an impact because for the most part, we can do all this stuff still, just a little bit less efficiently. And then you need to be able to read LSAS memory, which is kind of a big caveat when you're talking about being able to exploit things, right? So, well, not exploit, sorry, just when you're pen testing or moving through something. But the reality is that, like, in 2016, again, everybody runs Mimikatz and things like that. Getting access to LSAS isn't that hard if you have administrative access to the box. But it does mean that this is probably a little bit more useful in a forensic context than it is anything else. So, and with that, let's get back to the demo. So I'm going to simulate, again, capturing RAM. And then after we get that, I'm going to run the recall plugin. So there's a screenshot there of the volatility plugin. And then I'm going to basically, just to show you both, I'll go through recall as well. And hopefully that will work. Okay, cool. So we see that it dumped out this single session ID. And again, the reason that this is, there's only one is because I'm not connected to the internet intentionally. So that's the only one that's going to be there is from that RDP session I made. So we're just going to copy that into this demo file and read it out of the file. Hopefully. No. Don't tell me copy paste failed. Okay, hold on. Sorry, live troubleshooting. What's that? Restart what? Okay, I got you. Okay, cool. Oh, the joys of open source software. Oh, we're so close, and it's not even the hard part of the demo. This is like literally the basics. No. Okay. Hold up a sec. Let me just see if... what do I have mounted, actually? How much time do I have? I know. See, I shouldn't have antagonized them. That was my own fault. Okay, so tell you what. Since we already have it, let's just. Do you guys mind if I reboot Kali really quick and just see how that goes? The extended demo, just because you're my favorite audience. In the meantime, if anybody has questions about anything, please feel free to come up and ask. The microphone's up front.
In Windows 10, Microsoft started doing virtualization-based security to grab some of the LSAT secrets and put them off, like protected by the hypervisor.
Worst place for that to happen. Sorry, go ahead.
Have you looked to see if that affects any of the data
So-
you were able to pull?
Yeah, so I guess what I should say is I've tested this with Windows 7 and I've tested it with Windows 8.1, but I mostly was working on Windows 10 in the Server 2016 preview. And the hardest part was really the session tickets because I don't really know. I wish that if there's, I just want to make sure that I'm doing it right, so I wish that there was a way that said this is exactly how it should be done. But yeah, no, everything was done on Windows 10.
Was Hyper-V enabled?
What's that?
Was Hyper-V enabled?
No, I don't know. Probably not, no.
Okay, cool. Oh, yeah, credit card, yep.
Okay. God. Okay, well, apparently I'm not going to get that functionality, so I'm going to spare you me standing up here and typing it by hand. But if you want to see the demo, I guess come to me afterwards and I'll show you. Bullshit. Okay. So yeah, anyway, that's basically, this is, you can also see it in Wireshark and just see the keystrokes going across, which is what that is. And that's it. So you can find me on tinrabbit _ on Twitter, and then thanks to these people for all their help. I really appreciate it. So that's it.